Hello everyone, Yuriy Reznik here from Brightcove, and today I'll talk about gaze-driven video delivery. Science fiction or viable link to the metaverse. The talk will have few parts. First, I'll introduce the main idea of this technique. Then I'll talk about underlying principle, why it might work, what its potential, what are the challenges. And then I'll talk about what could potentially be done, if not today, but then in the next few years and certainly in the next decade, to try to bring this idea to practice. At the end, I'll have some conclusions. With this, let's start with the key idea. The idea belongs to Bernd Girod, who is currently professor at Stanford, and back in 1988, he published a very fascinating paper. It was called Eye Movements and Coding of Video Sequences. And what he envisioned in this paper is a system where traditional video delivery with encoding, decoder, monitor, and network somewhere in between is augmented by an eye tracker that tracks a viewpoint or gaze point of a viewer at each point of time, and it transmits this gaze point to encoder. And the encoder then uses that gaze point information to do some magic, improve video encoding, and send video that is now relevant to this gaze point and improve performance quite dramatically. So underlying principles why this idea might work. Well, first and most important is the sheer fact that our vision is highly asymmetric. If we look at topology of retina in our eyes, we realize that vast majority of cones is concentrated in a very tiny spot, which is called fovea. If we project the spot in view field, what we realize that it corresponds to just 1 degree of viewing angle out of about 120 in full field of view. Only that 1 degree that we see with high accuracy. The rest we see with much lower spatial resolution, because outside of this spot, the density of cones is going at much lower level. Talking about orders of magnitude of density, orders of magnitude loss of resolutions in peripheral vision versus foveal. And the second phenomenon that is important is understanding how our eyes move. And it turns out there are different types of eye movements that are important. First is smooth pursuit. These are types of eye movements that correspond to us looking at certain objects and try to follow them as they move. For example, it could be a ball moving during play of football players, or a face of some actor during a scene in a movie. But we can follow moving objects only up to certain speed and to certain velocity. We can't see, for example, bullets flying next to us, right? The limit of velocity of smooth pursuit turns out just about 20 to 30 degrees per second. If things moving fast, we can't follow them, we lose them. What happens with us moving certain objects, it's not only single eye that follows both eyes are moving, and that corresponds to additional type of motion activities, which is called vergence movements or vergence shifts when both of our eyes locked in certain objects. The other type of eye movements that is important is called saccades. It's almost random looking periodic scans of view fields that our eyes are doing, and what happens during almost like a reset process, where at the end of this seemingly random scan we again lock on some object and keep following it. They happen periodically, but we don't see things clearly during saccades. We just try to figure out what would be the next interesting object to follow after saccade end. Now, what is important also as a phenomenon is that when our eyes are moving, that does have a certain effect on our sensitivity to some artifacts. For example, blur, noise. There is also effects on contrast, masking capabilities during movements versus non-movements. And these effects help to achieve certain things in Turing encoders. But fundamentally, out of all these factors, the one that stands on the top is just sheer eccentricity of vision. The fact that we can see things clearly in a tiny spot, that by itself is a huge factor that is just crying to be exploited. And what potential it brings? Well, as we realize, if we just can see 1 degree of viewing angle, full degree in TV systems, as we know, is about 30 degrees. What it means? It means that we have potential of about 500x reduction in pixel count. By the way, that 1 by 1 degree of viewing angle, what it should correspond to in terms of pixel resolution. Well, if acuity is about 30 cycles per degree or 40 cycles per degree, you need about 80 by 80 pixel patch to cover it. Well, maybe 100 by 100 if sort of looking at people with higher acuities than usual. Tiny compared to what we typically see today, right? If you look at the Ultra HD systems with recommended wider viewing angles, well, the savings potential is indeed even higher, up to 2000 x reduction in potentials in terms of pixels. And if we're talking about immersive system, virtual reality headsets, kind of Metaverse interface devices, we're talking about 8,000x reduction in resolutions that might be sufficient if we know where the person is looking at each point of time, and we could exploit this information instantaneously. So bottom line here is this. This idea has huge potential, but it requires zero delays in communicating information about gaze point and assumes perfect accuracy of gaze tracking or eye tracking. And it also assumes perfect reaction of the system on it. But question is it practical? Can it be potentially reduced to practice with some approximations, with some relaxations and delay constraints and so on? So it turns out it could. And first thing we need to understand is what would be the impact of delay. So if we allow information about gaze point to communicate to the receiver and the reaction to this gaze point to have certain total latency of delta of tau, what it means? It means that if we knew that gaze point was in one particular point, then by the time we receive video in which we already assume that gaze point, well, our eyes will be looking somewhere else. And the distance between that original gaze point to our new gaze point, it actually could be computed. Let's say that this distance, angular shift, so to speak, or let's call it delta, it could be computed as tau times v, where v is the velocity of eye movements that happen during this period. As we talked earlier, there is a limit of velocity for smooth pursuits. So we could plug in 30 milliseconds, 30 degrees per second as one of those limits here. And if we also realize that this shift could happen left or right or in any direction, what it means that if we are trying to define now a region that would be a safe region to capture where the gaze point should be, relevant to where we detected it, well, that size of this region, which we call RI width here, could be computed. It could be limited by 1, which 1 was the original width of the foveal region, plus 2 times this delta that we just computed, 2 times V max times tau, and that gives us a formula. And what this formula tells us? It tells us that, let's plug some numbers. So if the delay in the system was 0 second, boils down to a region width of 1 degree. Same exact as it was in our earlier assumption when we think that we only need to cover the foveal region. When delay in the system is 33 milliseconds, it turns out that sufficient region that we need now to cover is about 3 degrees of viewing angle. So that's wider than 1 degree, but it's still tiny compared to, for example, 30 degrees. So it's still quite meaningful in terms of potential of reduction of pixel count. Now, if the delay is, say, 66 milliseconds, what it means that our region of interest should be about 5 degrees. And 5 degrees is still reasonably small, so still we will have very significant potential of reduction of pixel count and bitrate if we use the system. So 30 to 60 milliseconds, 33 to 66 milliseconds give us pretty reasonable range of operating points where we could see some good potential. But what if delay is, say, 500 milliseconds? Half a second is pretty common today. Well, it turns out that in this case, this region will have to be 31 degrees, which is about the size of the screen that we have today when we send videos to TV systems. So the morale here is this: we have long delays. There is no free lunch. This system is not gonna help much. Delays are long. It's 500 milliseconds beyond sending videos the way we send them today is probably the best regime to use, and certainly the simplest regime to use. But if we can build systems where delays will be about 30 to 60 milliseconds, that opens up opportunity to use this idea and use this phenomena and achieve quite dramatic gains in compression. Now, some consequences. If delays are about 36 milliseconds at 30 to 60 milliseconds, what it means? It means that communication radius will be limited. Even if you send signals with speed of light, they will only travel as much with this delay allowed. It turns out that radius becomes about 4,000 to 8,000 kilometers. In comparison, the circumference of Earth is about 40,000 kilometers, order of magnitude longer. So you can't use this type of a system to communicate to somebody on the other side of the Earth. It will have to be local. It will probably work well for last link or within a small country, but not on longer distances. Of course, to get to a 60 millisecond delay, we will need to do many other sacrifices and constraints. Encodings probably will be only intra encodings. Frame rates in cameras will have to be much higher. 30 millisecond entire delay, you can't sample at 30 frames per second. You need to sample much faster. At least 60 frames per second, maybe much beyond that. Then, of course, no other buffers, likely need for cross-layer design and so on. But if we look at this again and try to think what can be done, how the system can be designed more pragmatically today, turns out that it actually could be designed in assumption that we don't build system to do impossible. So the system will only utilize this technique at last link level communication between user device and some intermediate edge server or relay or gateway, and then communication between that gateway and another terminal or regional source of the content. That communication will require full representation. So if we start with this as an assumption, then we actually can build systems. And then we can actually build it in a very neat way. For example, what we could do is we could simplify our logic on this intermediate gateway that communicates with user device. We could build a system in a way that the spatial information about video is partitioned in many tiles, and where the information about gaze point will translate into effectively selection tile or a subset of those tiles from the video frame, and sending only those tiles as opposed to sending entire frame to the receiver. The other interesting element of the system that probably will be worthwhile to put in place is that in addition to transmission of just tiles corresponding to gaze point, what we will also need to send is we'll need to send a low resolution version of the entire frame. And why it's important to send is because outside the foveal region, we still have cones, they sparsely positioned, so their spatial resolution is very low, but they still react on video temporally with full accuracy. So to have this temporal continuity in a broad field, it will be quite wise to send the low resolution base layer, as they call it, this full frame rate and the entire view field. So there will be a composition of this base layer sent, which of course could be encoded at, for example, 1/10 of the original resolution. So bitrate wise, it's orders of magnitude lower, plus of course the tiles capturing region of interest. We also assume the system will cover a very small fraction of the full view field. So the savings still will be very significant, orders of magnitude. And so this could reduce potentially the complexity of edge server, and of course, the user element could also be pretty simple, putting all this information together and rendering on the screen. But of course, the link has to be super fast with low delay, and the user element will need to manage it all with extremely low delays as well. No retransmissions, no buffering, no delays anywhere. So building the system will be a lot of fun, but as we can see, it seems that overall design could be crafted quite nicely to make it practical. And with this, let me bring some conclusions. So this idea clearly belongs to the future. If we're stuck with 500 milliseconds and beyond, well, realistically not going to help today. Sending videos the way we send it today is the right thing to do things. But if we want to be creative, we look next few years, maybe next decade, who knows, maybe systems like this will emerge as quite viable for many applications. Maybe Metaverse will be one of them. If reducing the bandwidth at the last link and building system in super scalable fashion at the last link is important. If we are going to immersive systems where we need to send all 120 degrees and there's only other ways to increase pixels, this technique has just even higher appeal in those types of applications. And potential is just phenomenal. And of course, whole system design promises to be a lot of fun. So with this, I hope this was useful. Thank you very much for your attention and enjoy the rest of the conference.